All right. Hello, class. Um, I am pre-recording the AP Physics C week of May 3rd lesson. And I'm currently making spaghetti for dinner. And so I may have to run into the kitchen to turn the heat up or turn the heat down or make sure that the house doesn't burn down. So keep that in mind. All right, so let's get right to it. So the first thing I want to do is I want to review the magnetic field due to a wire. And so you might recall that there was a right-hand rule number 2, which is to figure out the magnetic field from a wire. Okay. And what that says is that you take your right thumb and you point your right thumb with the current, and then your other fingers curl around the current like the magnetic field does. Okay? Because the magnetic field lines always do loops. All right? Okay? So, for example, what if we have a current that is going upward? Okay, so I would take my right thumb and point it upward, and you can see that my fingers are curling in this sense. So on the left side of the wire, the magnetic field is pointing out of the page. And obviously the magnetic field is going to be stronger closer to the wire. And then it curls back into the page on the other side. Okay? So that is for a straight wire, but the same kind of thing applies to if you have a loop of wire. So that's what we want to talk about today, is if we have a loop of wire, and let's say that the current is going around in the, so this would be the counterclockwise sense, okay? And actually in this lesson, we're going to be only concerned with the magnetic field inside the loop, okay? All right. And so I put my thumb in the direction of the current. So for example, on this side, the current is pointed up, and I can see that my fingers are curling out of the page. All right. So what that means is that inside the loop, the magnetic field is going to point out of the page. Okay. All right. And similarly, if the current is going in the opposite sense, so now it's going clockwise, in that case, I would put my thumb down, and I can see that my fingers are curling into the page. So inside the loop, the magnetic field points into the page. Okay, so this is going to be really important for this lesson. And I can actually remember being in high school and teaching. I was in an AP Physics class, and my friends didn't understand this fact, and I remember trying to teach it to them, and eventually they got it, but they had a really hard time understanding the magnetic field due to a wire. Okay, so what we're going to be talking about today is something called Faraday's law of induction. Okay. And so a really important part of Faraday's law of induction is the concept of magnetic flux, which is denoted by the capital Greek letter phi. Okay. And all right. So if you want to visualize magnetic flux, you've got some kind of a loop. Okay. So you have a loop, and that loop has n turns. So it's not just going around once, it's going around a bunch of times, n times. All right. And it has area A, so that would be length times width if it's a rectangular loop. Okay, so that loop has an area vector, which is, so this is the area vector of the loop, like we discussed before. And then there is some kind of a magnetic field that we would say is threading the loop. Okay, so the magnetic field is threading the loop, so there's a magnetic field that is passing through the loop. Okay, and that magnetic field makes an angle of theta with the vertical, or with the area vector. Okay, so the magnetic flux is going to be NBA cosine of theta. All right, so it's exactly the same definition as the flux of the electric field. Hang on a second. I'm going to check on my stove. Knock it off, bugs. Cool. So this is the exact same definition as the electric flux, only instead of electric field, it's magnetic field. And then in magnetic flux, if you have multiple turns, then each turn of the wire counts as a additional flux, okay, as a multiplier. If I wanted to write this as an integral, you would write it as exactly the same, in exactly the same way as we did for electric flux. So you might remember that electric flux was the integral of E dot dA. And in this case, it would be the integral of B dot dA times the number of loops. Okay? So, all right. Now, obviously, the units of magnetic flux are going to be we can see that it's a magnetic field times an area times two things that are unitless. So that's going to be Tesla meters squared. Is the units of the units of magnetic flux. Okay, so what Faraday's law of induction says is that a changing magnetic flux induces so a changing magnetic flux induces, now induce is a word that means like creates or causes, okay? Like if it doesn't get used a lot, but the one place where I can think of it being used is when someone is having a baby, right? You can induce labor, That means if the baby doesn't want to come out, you induce labor. That means you give the mom an injection of something that makes them start having the baby. Okay, I don't know what the chemical is, but there is some chemical. So induce means to cause. Changing magnetic field induces a voltage, okay, in the loop. Okay, so it's weird. It's like a changing magnetic field makes it so that it's like there is a battery in the loop. Okay, even though there is no battery, or there could be a battery, but it acts like an additional battery. Okay, so the changing magnetic flux induces a voltage in the loop. Okay, and that induced voltage is called the induced electromotive force. Also known as the induced EMF. Okay, so again, a changing magnetic flux means that there's going to all of a sudden appear a voltage in the loop, even though there might not be a battery in the loop. Okay, and that voltage, depending on the amount of resistance the loop has, is going to cause a current. So current will flow. All right. So this is the basic idea of Faraday's law of induction. I haven't given you the actual mathematical equation, but just yet. So how could we change the magnetic flux? Well, we can see that it depends on four things. The number of loops is usually fixed. Okay, so that doesn't change. But the strength of the magnetic field could change. That would change the flux. The area could change. So that means that the loop gets bigger or smaller or changes shape. Okay? Or theta could change, which means that the angle the magnetic field makes with the so the magnetic field changes directions. That is also a change in flux. Okay, so what I want to figure out is what is the direction, what is the sense of the induced current. Okay, and I'm going to go check because I hear the pot is boiling over. Okay. And so the idea is that, two people were watching. I don't know who JBCX is, but hello. So what is the sense of the induced current? The induced current opposes the change in flux. Okay? So what that means is that loops do not like the flux to change. Okay? So what that means is that loops, I should say, how should I put this? The induced current So basically what will happen is there's an external magnetic field. The external magnetic field changes And then the loop says, I don't like the magnetic field to change. So there's going to be an induced current. And so the loop will make its own magnetic field that attempts to cancel the change. Okay? So that's how it works, is that the loop will have a current that cancels the change. It won't completely cancel it, but it'll partially cancel it. Okay? So the induced current makes the loop create its own, should not be an apostrophe there, but magnetic field to cancel the change. All right. So let's do some examples. Okay. So we've said nothing about what is the size of the induced current. All right. So don't worry about that just yet. Okay. So what if I have a loop, and the loop initially has no current, and there's a magnetic field that is out of the page. Okay. And then maybe that magnetic field changes so that it's more intense. Okay, so I am going to draw more lines, more density of lines, because remember, the density of lines is the strength of the magnetic field. Okay, so now we have more lines going out of the page. Okay, so we have flux out of the page, and then it becomes more flux out of the page. So the loop says, I liked the flux the way it was. Okay? So the loop is going to try to reduce the amount of flux by creating its own magnetic field into the page, because that will cancel out the increased out of the page flux. Okay? So it's going to make its own into the page magnetic field that cancels out the other one. So the current is going to go clockwise. So the induced current will go clockwise. All right? What if we had a situation where the magnetic field is out of the page, and then later on it reverses directions? So it goes from out of the page to into the page. Okay? So the loop says, no. I liked the flux when it was out of the page. You made it change to into the page. So I'm going to try to cancel out that change and make my own out of the page magnetic field. Okay? And we can see here that if the current flows in the counterclockwise sense, that will create a magnetic field out of the page. So the loop will have a counterclockwise current that will partially cancel this change in flux. Okay? So that's the way it works. So this is tricky, all right? It is tricky. Once you understand it, it's easy. But at first, it is tricky. So I would strongly recommend, okay, I would strongly recommend that if you do not understand what I just said here, that you look up other videos on YouTube about Faraday's law of induction. I'm sure there've got to be some that have really fancy graphics and things like that to demonstrate what's happening, but I don't have that capability. All right, I'm making dinner at the same time, making spaghetti. All right. Well, I haven't put the spaghetti in yet, but I'm making the sauce and I'm getting the water boiling. Okay. So Look it up because it's tricky. All right. Oh, another thing that could happen. Let me talk about this. All right. Is oh, and that was a great example if I was speaking Spanish where I could use subjunctive. If I say, I recommend that, and then I could say the next thing in subjunctive. Cool. Okay. Another thing that could happen, so this happens sometimes, is you have a loop that has no flux, all right, but the loop is headed this way. Okay, it's headed to the right, and so it travels into into a region where there is now a magnetic field. Okay, so later on, now the loop is in this region with a magnetic field. So the loop has moved into a place where it now has a flux into the page. So the loop says, I don't like that. You made me have into the page flux. So I'm going to cancel that out because I used to have no flux. So now I'm going to make my own magnetic field out of the page. And the way to do that is to have a counterclockwise current. Okay? So, yeah, so that can happen. And then just one more example. Oops. I guess I'll do this other example on the next page, which is if you have a loop that is moving through a region where the magnetic field is constant, then even though the loop is moving, the magnetic flux isn't changing, right? Because it's still the same magnetic field, it's still the same area, it's still the same angle, okay? So in that case, you are going to have that there's no induced current. Okay, so let me actually state the Faraday's law of induction, okay? So there's a symbol, curly E, and curly E is the induced EMF. So remember, EMF is a voltage. So basically, this is the size of the battery. So even though there isn't really a battery in the circuit, it will behave as if the circuit will behave, or the loop will behave as if there is a battery. Okay? And this is the size of that imaginary battery, if you will. And it's equal to minus the rate of change of the magnetic flux. Okay? So that's it. So really, so this minus is representative of the fact that it is in opposition to the change. All right. So I want to do one example, which is actually we're going to do two examples, which is a generator. A generator. Okay. Give me 1 second. I'm going to check on my pasta sauce. Okay. So a generator. You might have a generator for when the power goes out. How does a generator work? Well, you have a loop. So let's say that it is a square loop. Okay. And that loop has a width W, or I guess a height H and a width W. Okay. and it has n turns. Okay. There's a magnetic field. We'll say that the magnetic field is constant and it has strength B. Okay? And you take the loop and you spin it with a constant speed. So there's a constant angular velocity omega, which is, remember, the rate of change of the angle. Okay? So in this case, so as I said, if we look at the definition of flux, if the flux is changing, then one or more of these three variables has to change. We have a constant magnetic field, we have a constant size loop, but it's the angle that's changing. Okay? So the induced EMF, all right, well, let's just write an expression for the flux. So the flux is going to be, all right, so the flux is going to be NB, area is height times width, times cosine of the angle, but the angle changes as time goes on, so it's omega t. All right? So then the induced EMF is negative the derivative of that. Okay? And so taking the derivative of cosine gives you, all right, negative the derivative of cosine gives you sine. Well, the derivative of cosine is negative sine, but then we cancel it out with this negative, and then the chain rule brings out a factor of omega. So you get n omega b h w sine of theta of omega t. Okay? And that is the induced EMF. Now, what I really like about this equation, okay, notice how the induced EMF depends on time according to a sine function, okay? This is why our power grid is AC, alternating current, okay? Because when we generate power, when we generate voltages to use in our home, we do it in exactly this method. We have a loop in a magnetic field, and something spins that loop. Okay? The thing that spins that loop could be, if it's a coal plant, it's going to be burning coal, spins the loop. That's where the energy comes from. Okay? If it is a hydroelectric plant, it's moving water that spins the loop. If it's a wind turbine, then it's moving air that spins the loop. Okay? So something external is spinning the loop. And we can see that when the loop gets spun, it generates a sinusoidally varying voltage. Okay? And that is why our power grid is like it is. Okay? It's because this is the method of generating power. So it's like, why change it to DC unless you have to? Okay? We can also see how to generate the biggest EMF possible. You want to spin it fast. You want it to be in a big magnetic field. You want it to have lots of turns. Okay? So it's an engineering problem. How do we optimize the induced EMF? So I think that is pretty neat. Another example is, okay, so let's suppose we had a, this one's going to be tricky. All right, so, well, I'm not going to make it tricky. I'm going to make it simple. So maybe you have a magnetic field that's pointing into the page, okay? And so this in itself is not a loop, okay? But what if we put a bar across this. Okay, so this is metal, and this is metal. This is a metal bar that's laying across. Okay, and so this metal bar completes the circuit, but the metal bar can slide. So see how the amount of area that is within the loop can change depending on, so the amount of area of the loop changes. If the bar is over here, then this area is greater. Okay, so let's say that you pull the bar this way with a constant velocity. All right, you pull it that way with a constant velocity. The height is h, and the magnetic field is directly into the page. Okay. All right. So let's write an expression for the flux. And this is only one turn. You can imagine this wouldn't work with more than one turn, okay? Because you have this bar that's sliding, okay? So let's just say that this width is W, whatever that distance is. So our flux is NBA cosine theta. Now, the magnetic field is perpendicular to the loop, so that means that cosine of theta is going to be 1. The number of turns is 1. Area is height times W. So the flux is B height times W. All right? So now to get the induced EMF, I take the derivative of that, all right, which is, so minus the derivative. Now, if we think about it, the magnetic field is constant. The height of this circuit is constant. It's the width that's changing. So we get, when we take the derivative, we get minus BH dW dt. Okay? And dW dt is the rate at which the bar is moving, which is its velocity, right? So we get minus BHV. That is the induced voltage. We could figure out the sense of the induced voltage in the following way. Notice that as we pull this thing to the right, we're making the area bigger. We're getting more into the page flux. Okay? So the loop says, I don't like more into the page flux. I'm going to make my own out of the page flux to cancel that change. And so it will make an electric current that goes this way because that sense will create a magnetic field that is out of the page. Okay? I did want to do one problem, and this doesn't even involve Faraday's law of induction, but it is in the homework, and I think it could trip you guys up, which is what if, or this is calculating flux with a non-constant magnetic field. Okay, so what if we have a loop that looks like this? Okay, so it has a height h and a width w. Okay, and we're going to call this x equals 0, this left side of the loop, and so this would be x equals w. All right, now the magnetic field is a function of x. Let's say that it is a constant times x. So what this means is that x equals 0, the magnetic field evaluated at x equals 0 is magnetic field at x equals 0 is 0, okay? the magnetic field at X equals W is, oh my gosh, getting a phone call, going to decline it, is going to be CW, okay? So that's how that works. So the magnetic field is getting stronger as we move to the right. It doesn't matter what direction it points. Let's just say it points out of the page. So it's getting stronger as you go to, so more dots as you go to the right. So how do we calculate the flux? Well, in this case, we have to use an integral. So the flux is and it's one loop, so we won't worry about the factor of n. Excuse me. The flux is B dot dA, and we have a loop that is perpendicular, okay, to the loop. So this is just going to be the integral of B dA. All right. And the magnetic field is a constant times X. So the question is, well, what does dA mean? Well, the area of a rectangle is H times W, okay? Or let's just say a rectangle of width X. So we'll say H times X. All right. Then taking the derivative of that, we get dA equals H dx. So why did I not take the derivative of H? Because the magnetic field does not depend on H. It depends on X only. Okay? So I don't need to take the derivative with respect to H. I only need to take the derivative with respect to X. Okay? So this is dA, so we're going to put that in right there. And I'm going to put this in for C. Okay? So I get the integral of Cx times H dx. And that integral is going to go from 0 to W. All right. So the C and H are constants, so they get factored out. This is just going to be W squared over 2. So I get CHW squared over 2 is the flux. Okay? So that is how you calculate the flux if you have a spatially varying magnetic field. All right, and so that is going to be important for one of the problems on the homework. So that is my lesson for today, and this is a tricky subject to wrap your head around, so don't be afraid to ask me questions in office hours. So I'm getting a phone call, so I guess that means I should end my lesson now. Okay, bye-bye.